Okay, so last speaker of this morning is Bischoff from the University of Oxford, and he will talk about Brane quantization of Toric Poisson varieties.
Great. Yeah, thanks a lot to the organizers for inviting me and also for being so accommodating, changing the schedule for me. So, okay, so what I want to talk about today is a joint project with Marco. And it's kind of going to be in the same kind of vein of Leonard and Marco's talks already. But what this is about is to try to get kind of a geometric approach to non-commutative geometry. And this is kind of a problem that has been around since the beginnings of generalized geometry, I think. So I just want to start by maybe just reviewing what is a generalized complex structure. So for me, I'm going to take it for today just the most simple. It's just a complex structure on T plus C star. So it's just an endomorphism that squares to -1, and it's integrable with respect to this natural bracket that exists. And generalized complex structures, they kind of generalize both complex structures and symplectic structures. So they kind of put them to a unified framework. So here's the two examples. If you have a symplectic structure, right. So I'm writing these things as kind of block diagonal T, T, and T star. Okay, so if you have a symplectic structure, it gives you a GC structure in this way. And also if you have a complex structure, you can do it like this. And okay, so the kind of the motivation for this project is that we'd want to have something like a category of generalized boundary conditions for a GC structure. And the idea is it should generalize what already exists for symplectic and complex structures. For symplectic structures, you have the A model, which is often defined to be the Fukaya category, where the objects of the category are Lagrangians in a symplectic manifold equipped with local systems. And there's also supposed to be these more general coisotropic branes that were discovered by Kubusin and Orlov. And those will be important later in the talk. When you have a complex structure, what you have in this case is the B model, which is, you can think of it as just the category where the objects are complex submanifolds equipped with holomorphic vector bundles. Okay, so what about other GC structures? So there's kind of a clue here, which is that if you look at the deformations of the A and B models, they actually match the deformations of the symplectic or complex structure as GC manifolds. So here's the example for the deformations of the B model. It's the sum of these three cohomology groups. The one in the center, these are the ones that come from deforming the complex structure to another complex structure. But then you get these kind of two extra pieces, and those are the things that kind of genuinely take you to generalize complex structures. And the ones that I'm most interested in are these ones here, the H2, the H0 of the wedge 2T. So those are the holomorphic bivectors. So those correspond to Poisson structures. So those should give you kind of non-commutative deformations of the category of vector bundles. So here I just want to recall how a holomorphic Poisson structure gives you a GC structure. So a holomorphic Poisson structure, it's just a bivector, so wedge 2T. It has to be holomorphic, so that's this equation here. And it has to satisfy an integrability condition, which is that if you bracket it with itself, with the Schouten bracket, you get 0. And out of a holomorphic Poisson structure, you can get a deformation of a complex structure, kind of deforming it as a GC manifold. And the way that you can do it is quite simple. You just take your holomorphic Poisson structure here, and you write it in terms of its real and imaginary parts, P plus IQ. You take Q, the imaginary part, and you just stick it in the top left corner. And that works for any value of parameter, I guess real parameter H bar here. That gives you a genuinely non-complex and often non-symplectic GC structure. And the idea is that, well, we'd like to define a category of branes for this GC structure. And the idea is that when we kind of turn on H bar, this category of brane, it should give kind of a non-commutative deformation of the category of homomorphic vector bundles. So there's kind of difficulties with this, but I just want to kind of ignore and just show what you could get out of this. So for this, I want to just recall, first of all, the geometric quantization of a Kähler manifold. So here M omega is a symplectic, compact symplectic manifold, say, and we're choosing a pre-quantization. So it's a unitary line bundle equipped with a connection whose curvature gives you the symplectic structure. And then to do geometric quantization, usually you need to choose a polarization, which is kind of selecting certain sections of your line bundle. And a popular choice is a complex polarization. So that's a complex structure that satisfies this equation here. So this equation, you can kind of read it in two ways. You can read it on the one hand as saying that with respect to the PQ decomposition that the complex structure gives you, your symplectic form is type 1,1. Another way of thinking about it is if you take, say, T 0,1, the 0,1, kind of the anti-holomorphic tangent bundle, then it's actually Lagrangian with respect to omega. And so if you take the sections of the line bundle that are kind of flat along this direction, those are exactly the holomorphic sections of the line bundle. So that's here, the global holomorphic sections. That's supposed to be the geometric quantization. Okay, so when we define this geometric quantization, the complex structure is kind of playing an auxiliary role. It's just telling us which sections to select. And so really, the quantization doesn't really encode or reflect the complex structure that much. And in good cases, the quantization will even be invariant under deforming the polarization. So if you want to encode the complex structure, what you should do is quantize not just omega, but all of the multiples, so omega, 2 omega, 3 omega, and so on. So those will be pre-quantized by all of the tensor powers of the line bundle. So you can take all of their quantizations and then just add them up together, and you just get this big thing, which now is the structure of an algebra, the homogeneous coordinate ring. And this algebra, it does actually remember the complex structure because of the Kähler embedding theorem. It tells you that this algebra, it kind of it gives you an embedding of M into a projective space. So the idea then is if we deformed our complex polarization to kind of this generalized complex polarization, whatever that means, then well, maybe the individual terms would stay the same, they would be unchanged, but the product would deform in a way that reflects the complex structure. And that would give you a quantization of the Poisson structure. Are there any questions about this so far? Motivation. Okay, great.
Why do you expect the space to be the same, the vector space?
Well, maybe in general you might not, but I'm just saying, you know, in good cases at least, you'll have this invariance of the quantization under changes of polarization.
Yeah, but I mean, once you turn on the H bar, why do you expect this to have the same vector space?
I don't have a good reason. It's
You're still quantizing the symplectic form. It's unchanged. Roughly speaking.
Do you have a projectively flat connection on this bundle of quantizations in some sense?
No, well, I guess I don't want to go into that direction. This, I mean this as kind of a motivation. Okay, so I want to kind of explain now how would we actually do this deformation? And to do this, I just want to reformulate the definition of the homogeneous coordinate ring from the perspective of the complex structure. So in terms of the B model. So we can give a definition of this thing just purely in the category of holomorphic vector bundles. And the way it works is the following way. So you have these two structures. I'll write them here. So you have, well, O is just the trivial vector bundle, the trivial line bundle. But what you get from this pre-quantum line bundle L is you get an autoequivalence of the category. So you can take any holomorphic vector bundle or coherent sheaf and you can tensor it with L. And what you do, so let me just here, if we apply phi to the n, phi kind of n times to the trivial bundle, so we're just tensoring the trivial line bundle n times with L, we just get L to the n. And then if we look at the homomorphisms from O to L to the n, that's just the same thing as the global holomorphic sections. And so that gives us the vector space, but the product is also kind of given by composition, right? If we had something going from like O to L to the n, say this would be like B, and another one O from L to the m, say A, well, what we could do if we wanted to multiply them, we would say apply the functor n times to A, right? So that would give you now something like that, and you just compose them. So that's where the product comes in. And yeah, so the point is that now that we've kind of expressed it this way, it's kind of clear that if we want to deform this, but when we turn on the Poisson structure, what we need to do is deform the category and deform this trivial line bundle and deform this autoequivalence. And then the same procedure, exactly the same procedure, would give you the deformation of the algebra. So this category, it's not kind of quite well defined, but there's kind of, it's partially defined. So first of all, the objects, they were defined, in fact, in Marco's thesis. And so the objects, so I'm just going to give you kind of one version of the definition of what is an object of this category. So it's called the generalized complex brane. And one way of defining it is like this. So a brane on this GC manifold, which is the one coming from the Poisson structure, it's defined again to be a unitary line bundle. But if you look at the curvature F, it satisfies this equation. So this is similar to the equation I showed earlier in the geometric quantization. It's kind of a deformation of the 1-1 equation for F. So if we set Q equals to 0, that would just say that F is of type 1-1. But now it's been deformed with the Poisson structure. And another thing to notice is that there's always a trivial solution, which is taking F equals to 0. So that means we always have this kind of trivial brane. So that means so far we kind of have the objects of the category, and we've kind of deformed one of the ingredients, which is the trivial bundle. The deformation of this autoequivalence is actually, at least on the level of objects, it also exists, and it's in a paper of Marco's called Branes on Poisson varieties. And he proved this theorem here, which is, so say we have our holomorphic pre-quantization of the symplectic form omega, so what I was just telling you about earlier. So the theorem says that if L admits a Poisson module structure, which it just means that if you look at the total space of this line bundle, this itself is equipped with a Poisson structure. It's kind of invariant in a C-star direction. Then given the structure, then this autoequivalence of tensoring with L, it automatically deforms to an autoequivalence. And so what that means then is that we actually, for free, get a whole bunch of GC branes. We just take this trivial one and we just apply this autoequivalence over and over.
To say again the definition of the category C sigma?
Yeah, so C sigma is it's not defined, but but the objects are defined. We don't know how to define the morphisms, and so it has many different types of objects. But these are examples of objects. So it's more general than this. But for example, an object would be a unitary line bundle whose curvature satisfies this equation.
But how can we state that with autoequivalence we don't have the categories? It's still possible to.
So we have it defined on objects. So what I'm saying is that if I know how to solve this equation if I have one solution to this system of equations, I know how to produce more by applying this C. And
No, only I was unclear to me whether this notion of autoequivalence is defined if we only have the objects as a category.
yeah, that's right. So it's just defined on objects, but the idea is that this category should exist, and in that case, this would be part of an autoequivalence.
Okay.
It's kind of a hope. Okay, and maybe I have time, I think. The construction of this autoequivalence is quite simple, so I was just going to kind of say a couple words about it. The way that it works is quite simple. So L was this unitary pre-quantization. So it has a metric on it. And let's call that metric H, and you can just think of it as a real function on the total space of L. And here nabla, this was the connection, but since L is complex, it's actually the Chern connection. And then Q hat is what I'm calling the Poisson module structure. So remember, it's a Poisson structure defined on the total space of L. And so what you can do is you can just take this function, which is a function on L, the Poisson structure Q hat, and you can take the Hamiltonian vector field, which I'm calling W. So this thing is defined on the total space of L. What I'm doing here is I'm saying it actually descends to a Poisson vector field on the base, on M. And we can take its flow. And then the definition of this autoequivalence is that if we have a brane, say solution to the equations, then what we can do is we can pull it back by the flow and then tensor it with L nabla bar. And nabla bar is just an average of the Chern connection, averaged over this flow. Okay, any questions about this? Okay, so now that we have the deformed, the trivial bundle and also the autoequivalence, then in principle, we should be able to get the homogeneous coordinate ring just by the same procedure as I said before. But basically the major problem is that we're stuck now because we don't know how to compute the homomorphisms. So that's kind of the main problem, and it has existed since kind of the beginnings of the subject. So what I want to then, I guess, present is a paper with Marco where what we're doing is we're kind of trying to develop a new approach to the category of boundary conditions, which is kind of based on using the A model of an associated symplectic manifold. So we don't know how to kind of define the category directly, but we can kind of reformulate it in terms of a calculation in the A model. And in fact, even there, it's not kind of solved because it relies on another problem, which is how do you define homomorphisms between coisotropic A branes? So that's something that is not, it's kind of an open problem in symplectic geometry. So we have this kind of reformulation, and we can implement it in some cases in the case of doing the quantization of Toric Poisson varieties. So hopefully that's what I'll explain. Okay, so I want to start now by going back to the geometric quantization of a Kähler manifold, and I want to explain how you can kind of reformulate this as a calculation in the A model of a symplectic manifold. So here again, I have the Kähler structure up here, and the idea is that we're going to encode it as a pair of branes inside of the cotangent bundle of the manifold. So this is, I think, an idea that showed up in some of the other talks of Leonard and Marco, and it's an idea that goes back to Donaldson. So let me explain this. I guess it's going to be review maybe. And just because there's going to be lots of different symplectic structures, so let me just make sure that we're all on the same page. So omega is the Kähler structure. The cotangent bundle of M. Well, because M has a complex structure, this thing has its canonical symplectic form, which is a holomorphic symplectic structure, but it has an imaginary part, which I'm calling little omega naught, and that's the real canonical symplectic structure. Right? We can think of this either as a holomorphic cotangent bundle or a real cotangent bundle. Okay, so the idea is we're going to encode the Kähler geometry as a pair of branes. I think I have a picture here, maybe. So here's the kind of, in yellow is the cotangent bundle, and the picture is that we're going to put two branes. One of them is a Lagrangian brane, which is in purple, and the other one is a space-filling brane, B, which takes up the whole space. So I'll explain this here. So first of all, the Lagrangian brane, it's just very simple. We just take the zero section and we equip it with the trivial local system. So that's this purple thing L. The second one is going to be space-filling brane. So I should recall the definition. So this is something that was discovered by Poisson and Orlov. And the idea is that a space-filling brane for us, it will be a unitary line bundle with a connection. So here I wrote it as U nabla hat. And it's going to be a space-filling brane if, when we take the curvature, F, so F should be the curvature of nabla hat. If you take the curvature and you add it to I times this symplectic form, then this thing gives you something holomorphic symplectic. And in this case, the definition is we're just going to take the pullback of L with its connection, but we're going to then add the real part of the canonical primitive of omega naught. So we're going to take F. We're going to take pullback of the Turing connection plus factor. And the point is that when we take the curvature of that and add it to I times little omega naught, what we're going to get is this big omega naught, the holomorphic canonical symplectic form, plus the pullback of the Kähler form. So that's a magnetic deformation. And it gives you actually a holomorphic symplectic affine bundle. So that's the space in the brain. And this really kind of encodes the Kähler structure because we can just recover it by doing an intersection. Okay. And now the way that we're going to define the quantization, so this is kind of inspired by some work of Hukov and Witten. We're going to say that the quantization is going to be defined as the space of homomorphisms in the A model between these two branes. So from this Lagrangian brane to the space-filling brane. So this is an example of one of these calculations that's that is it's not quite well defined. So there is some examples in the literature where these calculations have been done, work by Albi Zaslow, Gukov Witten, Gukov Gayoto, maybe a few others. But we're going to give kind of a definition that will work in the cases that we care about. And it's going to be, the proposal is based on holomorphic geometric quantization. So the idea is,
What is the analog in the classical geometric quantization? So this would be what exactly?
this will be the geometric quantization of omega, right here.
So what do you mean by the geometric quantization? The Hilbert space?
Well, just the vector space, the one that
Yeah.
the global sections of L. Yeah. So that's what we're aiming for. And let me just say how we can get it. So first of all, this space filling Brane, we can modify the connection. So instead of adding the real part of alpha naught, we just add the full primitive of the holomorphic symplectic form. And this now defines a holomorphic line bundle, which gives a holomorphic pre-quantization of this holomorphic symplectic affine bundle. So we have here, yeah, so this is the holomorphic pre-quantization of the Brane. And then we need to choose some structure, which is a holomorphic polarization. So it's a foliation of the cotangent bundle by holomorphic Lagrangians. And in this case, there's kind of an obvious choice, which is just you just take the vertical fibers. Basically doesn't work. So we just take the vertical fibers in this case. And then the way that we're going to define this space of homomorphisms is we're going to take to be the holomorphic flat sections along the Lagrangians, so along the cotangent fibers. And I guess I'm going to say something that sounds strange in this case. I'm going to take, it's defined to be the holomorphic flat sections along the leaves that intersect L. So in this case, it's a bit strange because every fiber intersects L, so there's no condition. But later on, it will become a condition, and it will be kind of a crucial condition. Does the definition at least, kind of, even though it's a bit strange, does this make sense?
So those are like the Bohr Sommerfeld leaves.
Yes. Yeah. Exactly. Yeah. And in this case, there is also, yeah, in general, you would have a quantization condition on the leaves, but now all the leaves admit flat sections. And in this case, it's kind of clear if you just take things that are flat in the vertical direction, those are kind of constant. So those are pulled back from holomorphic sections of L. So you kind of clearly recover this. So that's how we get the quantization from this perspective. So what about the algebra structure? So this comes from the fact that the cotangent bundle, it's not just a symplectic manifold. It has some extra structure, which is the fact that, yeah, so the cotangent bundle, it has the addition of the fibers. And so if you think of the addition in this way, well, it's one way of thinking about it is it gives you a Lagrangian relation going from T star across T star, kind of have not a map, but a relation. Great, thank you. Oh, perfect. And the idea is that this structure, it endows the A model with the tensor product. So there's a nice paper of James Pascal's that explores the consequences of this. And so that means that our A model actually has we can tensor the Branes, and the unit for this tensor product is the zero section. And it turns out that if you to get these integer rescalings that I was telling you that you need, you can just get them by taking this original B and just tensoring it with itself. So we can just define the homogeneous coordinate ring like this. the maps from L to all the tensor powers of B. And then the product on the algebra is just the one induced by the tensor product. Okay, so that's how we get the homogeneous coordinate ring. And this is what we're going to be able to kind of generalize when we turn on a Poisson structure. So are there any questions about this? Okay, great. So
Does this space recover the vector space of the, the vector space underlying the algebra of the geometric quantization of the Kähler?
yes, exactly. If you follow this proposal, it does give you exactly the global homomorphic sections. Yeah, so I mean, we're not really doing anything except kind of we're reinterpreting the homogeneous coordinate ring as something, a calculation going on in the A model of the symplectic manifold. And it might seem kind of weird to just do this, but the point is that this will be able to be deformed when we turn on the Poisson structure. Yes.
Question. So in general, you would expect that this algebra, which here is just commutative, it acts on functions. I think here it would be just multiplication action. That's what it's commutative. But is this clear from this A model perspective why it acts with the algebra?
The algebra acts. What do you mean?
It comes with a representation. Maybe it acts on itself. I don't know. It should be acting on a Hilbert space because these are supposed to be operators.
I'm not sure that we're getting that. I mean, this is.
Is it Hom BB or something? You see what I mean?
I mean, really, we're just reinterpreting the homogeneous coordinate ring of a Kähler variety.
Right.
So I don't think this necessarily has to act on something. But I kind of see what you mean, but maybe we can talk about it later. Okay, so I just want to kind of explain, this is kind of speculative and heuristic, but it's kind of an idea for how you would define the category of GC branes. And the idea is to define it by using a monoidal A model of an associated symplectic manifold. And the associated symplectic manifold, it will be a symplectic groupoid associated to the GC structure. So here's how it works. So I mean, we saw here that this thing that went here, we stuck a Poisson structure. This is actually a general feature of generalized geometry. A GC structure, if you just look at this entry here, it's always going to give you a real Poisson structure. So it's kind of an underlying real Poisson structure that a GC manifold has. And this can be integrated to so-called symplectic groupoid. And you can think of this as kind of a moduli space of Hamiltonian paths in the manifold. So, I mean, maybe if you don't know what this means, you know, possibly the fundamental groupoid of a manifold, which is just all paths in your manifold, right, up to homotopy. This is just kind of the version of this that makes sense when you have a Poisson structure. So you just take Hamiltonian paths. And this has a symplectic structure. And so we can make use of its A model. But it also has a tensor structure because we can compose paths. So there's kind of a product structure. And so that will endow the A model with a tensor product structure. And the unit in this case, it's going to be given by the so-called identity bisections, which is like the constant paths. Okay, so yeah, so we now have an A model with a tensor product structure. So what can we do now? So if you take the kind of the source and the target of a path, the two endpoints, that defines a map from this G to M cross N. And if we equip M cross M with the generalized complex structure, well, remember, this is a symplectic manifold, so it's actually a GC manifold as well. And it turns out that this map, it's generalized holomorphic. And so as a result, if you have two branes, GC branes on your manifold, then you can take their product in here and just pull it back, and that will give you an A brane in the groupoid. So the idea is, well, let's just define the space of homomorphisms using the A model as the space of homomorphisms from this identity bisection to this Bij brane. And then the composition will be induced by tensor product. So this is kind of a heuristic idea for how we could define the category in general. And again, it still has this problem that it in general will require us to be able to define homomorphisms between coisotropics. Well, at least from a Lagrangian, something that in general will be a coisotropic. Although there's some interesting examples where you actually do get Lagrangians. Okay, so that's the general idea. And yeah, so for the rest of the talk, I just want to explain a particular implementation where we can construct the deformation of the homogeneous coordinate ring in the case of a toric Poisson structure. So I'm just going to kind of go through the steps that I outlined before in this concrete case. So okay, so let's start now with a toric Kähler structure. So if you want, it's the same Kähler structure as before, but now we have this Hamiltonian action of a compact torus. And this action, it can be complexified to a complex action of a complex torus. So the action of the complex torus, it's not Hamiltonian, but what we can do is lift it to a Hamiltonian action on the cotangent bundle. And this has a moment map, which I'm calling J naught. Okay, then for the pre-quantization, I want to choose it to be equivariant. So the total space of the line bundle will have a lift of the action of the complex torus. Okay, then what we can do is we can choose an R matrix, C. So maybe I should say, really it should be kind of C is in wedge 2 of the Lie algebra, S1 to the n. In fact, we could take it to be complex, but things simplify just a little bit in the real case. And given one of these things, well, we can just push it forward using the action, and it gives a holomorphic Poisson structure on the manifold, which is invariant under the torus action. And it automatically, because we have this equivariant pre-quantization, it automatically lifts to a Poisson module structure on the total space. So remember, this is basically all of the ingredients that we needed to run this kind of deformation procedure. So first of all, just from the Poisson structure, our complex structure will deform to a GC structure like this. And because of the Poisson module structure, it will deform the tensoring with L to this auto equivalence. And so let me just say a little bit how this works. Actually, well, so yeah, so in this case, this, remember this Poisson structure, it will have a symplectic groupoid. And the interesting thing is that in this case, it's very simple. It's just the cotangent bundle. The underlying symplectic manifold is the cotangent bundle. The only thing that changes is the structure maps. So, I mean, the idea is that you're kind of thinking of the total space, every point in the total space of the cotangent bundle, it kind of corresponds to a path on M. And so basically I need to tell you kind of, if this is a path, it should have a starting point, S, and an ending point, T. And these are just given by this formula here. So pi is the usual the cotangent bundle projection. You can see it's just deformed using the R matrix and the moment map. And the multiplication, which is like the composition of paths, is also deformed. And the kind of the key point is that because of how nice this deformation is, the A model will be unchanged, but the tensor product will be deformed. So here's kind of a picture. So the original cotangent bundle, it's the symplectic groupoid for the zero Poisson structure. And the vertical fibers, I mean, in this case, Hamiltonian paths, because all the Hamiltonian vector fields will be zero, you can't kind of move around. So that's why the source and the target have to be equal. So just get this, but now we turn on the Poisson structure and everything kind of gets deformed. So yeah, so we want to deform the homogeneous coordinate ring. And so we need to turn on this deformation. So here's how it works. So remember, the way that we obtain this was we used a Hamiltonian vector field, or sorry, a Poisson vector field, and we kind of averaged the connections. So that's what we're getting here. So this gives us the family of branes that are deforming the tensor powers of the line bundle. And then we just pull them back to get branes on the cotangent bundle. And the thing that happens in this case is actually these branes are actually the same ones that we had from before. So the ones that were originally the tensor powers of that original B, that's what we're getting from this procedure going back. And so that means that when we compute this algebra, the underlying vector space will remain unchanged because the Brane and the A model are the same, but the thing that will change is the product because we've defined the tensor product on the category. Are there any questions so far? So what I want to explain on this slide is just what is the kind of the geometry that kind of underlines this family of branes here. I mean, and the fact that they tensor, that you have a tensor product between them and so on. So the thing that underlines each brane is the structure of a pre-quantized holomorphic symplectic manifold. And in fact, these things are holomorphic symplectic Morita equivalences relating this Poisson structure to itself. And then the tensor product for these branes, it will translate into composition of these Morita equivalences. So whenever you have a holomorphic Morita equivalences, you can compose them, and that actually matches with the tensor product of the branes. And that kind of it kind of can be enhanced with the prequantizations. And here's the formula. So I'm not intending this to make sense, but just to see kind of what are the ingredients. So you have the moment map, and then you have this R matrix C. So you can kind of summarize by saying that kind of all of the structure of all of the branes with the prequantizations gives you a holomorphic symplectic groupoid equipped with a multiplicative prequantization. Okay, so now I need to explain how do we do the quantization. So, well, as I said, because the A model is the same, you should get the same answer as before, but I actually want to compute it in a way that will allow us to multiply. And the point is that we need to choose, so remember the way that we did it was through a holomorphic geometric quantization. And so we needed to choose a holomorphic prequantization of the brane and these polarizations. And the original one that we chose, which was the vertical fibers, it kind of no longer works because it's not compatible with the new product structure on the cotangent bundle. So you have to choose another one. And so that means that we're going to kind of do the same calculation, but with a different choice of a polarization. And the polarization we choose is just the one given by the holomorphic moment map. And in this case, it's kind of, well, so remember, the definition of the quantization is that we're supposed to take the holomorphic sections along the fibers of the polarization that are kind of Bohr-Sommerfeld and that intersect L. And kind of remember before, for the vertical sections, every fiber intersected L and it emitted a flat section. But for this new polarization, it's no longer true. So what you get is a quantization condition, first of all. Only some of the fibers of this map L actually emit flat sections. So those correspond to lattice points. And also not all of the fibers intersect this L. So that's kind of another condition. And here's a picture of what's going on. So you should think of before we were using the vertical lines, but now we're using this kind of new thing. And so we need to select only the ones that correspond to integer points in the image of the moment map, and also the ones that intersect L, and that corresponds to the fact that the image intersects the Dalzant polytope associated to the symplectic manifold. And so what you get when you do this is actually you get the weight space decomposition of the global homomorphic sections. So I mean, this is a case where it's actually key that we have this Lagrangian, right? Because it's giving us a selection criterion, right? We're not supposed to take all of the fibers, only the ones that intersect L. If we didn't do this, we wouldn't get the right answer. Okay, so in this case, yeah, we can carry out the calculation, and this is the result. So we get an algebra, and the underlying vector space, it's canonically isomorphic to the vector space underlying the homogeneous coordinate ring. But under this identification, the product gets deformed. If you take two sections, F and G, then their product is deformed in the following way. So it's kind of like a quantum torus. Okay, I think that's
Any question, Francis?
So how far are you from implementing this in other types of generalized compression terms?
So there's other cases of Poisson structures that we can sort of do, but that's still work in progress.
It's no longer holomorphic.
No, still holomorphic. Yeah. So I mean,
Okay, you're removing the toric acid.
exactly. Yeah. We want to remove it because there's plenty of kind of like Sklenan algebras that are associated to CP2 with an elliptic curve. So we want to be able to get these examples in this way. And there's we have kind of partial progress, but we haven't been able to make it work yet.
If we looked at real polarizations, is there a similar story with real instead of complex polarization?
What do you mean by real polarization?
Lagrangian foliation in the real sense.
Well,
so you are considering in classical case complexification of Landau bundle, and then you consider some Lagrangian foliation thereof that you could consider directly.
So here, I mean, this is a holomorphic symplectic manifold, and so we're kind of using like we're using kind of like a real polarization of a holomorphic symplectic manifold, right? Because we're using foliation by Lagrangians. But the thing that's maybe interesting about this particular one is it, well, if this gives you a foliation of the total space, right, by these Lagrangians, but if you intersect it with L, it gives you the real Lagrangian polarization of the underlying Kähler manifold coming from its moment map. So this is related to the real polarization of the original Kähler manifold.
No, I don't completely understand. I mean, there's this notion of Kähler polarization, which
Yeah.
I started with as an initial example. But there's also a notion of real polarization. You consider the Kähler polarization. That's what you generalize, as I understand.
That's
I mean,
true.
the geometric quantization of a Kähler manifold. That's the model.
Yeah, sort of. So I guess we're kind of taking this symplectic manifold and kind of viewing it as an object in the B model of its complex structure.
Mm-hmm.
And then we're trying to kind of map a calculation in that B model to an A model of another symplectic manifold. But one way of kind of thinking about it is if you want to think about it from the perspective of Kähler geometry, maybe, is that the kind of the complex polarization I is kind of playing a role of kind of building up this holomorphic symplectic structure. So it's true that this is kind of related to this kind of complex polarization of the original Kähler manifold. But what I was saying is that in this case here, this kind of holomorphic Lagrangian polarization of this total space is also related to the Lagrangian, to the kind of the real Lagrangian polarization of the original Kähler manifold. Because if you intersect these kind of red leaves with L, so remember L is the zero section, so it's identified with the original Kähler manifold. So intersecting this foliation with L gives a foliation of the original Kähler manifold.
Oh, that will be a real polarization.
Yeah.
Thank you very much.
So questions, comments?
Maybe let me make a comment related to that question. So when you look at this picture, you see that what we're looking at is the symplectic cotangent bundle of a manifold. It's real, it's a symplectic manifold and it has an A model. Okay. In this A model, there's two branes, the yellow brane, which is a space-filling brane, and the blue brane, which is a Lagrangian brane. These are just two objects in the A model. And you want to produce a vector space, which is the geometric quantization of the original manifold you started with. And the idea is that it's the holomorphism between these two branes that gives the Hilbert space. Okay. Now, how do you compute the homomorphism between a Lagrangian and a space-filling brane? Right? The strategy that Francis is using. The problem you see is that the people in the Fukaya category, they don't tell us how to compute morphisms from a Lagrangian to a space-filling brane. Okay, so our solution is, well, let's take that space-filling brane and break it up into a million different Lagrangian branes, which are actually holomorphic Lagrangian. So it's like a real polarization, but it's not really. I think it's silly to call it real when it's holomorphic. It's a holomorphic real polarization. I don't know what to call it.
Yes,
Okay.
but you do not complexify.
Correct. And so it all, the type of answer that you get, it all depends on what those red foliations are that you pick. If you pick the straight lines that go straight down, what you get is the holomorphic sections of L. And therefore it looks like you're using a complex polarization in the traditional frame point of view. If you use this red lines, you're going to get it's going to look like you're doing a real polarization traditionally. Right? So no matter what kind of geometric quantization you might have done in the olden days, it's all being represented here as a holomorphic Lagrangian polarization of the space-filling brane. It's unified into one formalism.
And this problem that you might not have sections, flat sections. In your talk, you mentioned at some point that you have two problems. One is that this L may not be intersected, and the other was that there are no
only some of these
sections.
Exactly, only some of these fibers of J, only some of these Lagrangians admit flat sections, and that corresponds to this kind of, they correspond to the integer points. It's like a lattice.
Yeah, so this is related to the holonomy of the connection.
Yeah.
Okay, so you take only those leaves which have trivial holonomy.
Yeah. And an important point is that, as Marco said, this polarization is kind of related to the real polarization, but the quantization that we get is still kind of canonically isomorphic to the homomorphic sections of L. So it's really on the same underlying vector space. I mean, this kind of approach of getting an algebra is kind of inspired by some of the work of like Weinstein and Eli Hocking and so on. And I think they're always able to get these, well, in some examples, they can get these non-commutative algebras, but it's kind of not clear how they relate to the original kind of algebra that you're trying to quantize. So here it's kind of important that it's living on the same vector space. So it's actually deforming the product.
So you mentioned in the beginning this problem that it's not very clear how to define morphisms in the category you want to define, but you have in some sense a proposal in some special setting.
Yeah.
And is it possible with this proposal to define some, have some approximation to the category you want to define?
Well,
some smaller objects, I don't know. Is there some way to make it into a category? This proposal.
I think, well, so the main problem is that we still need to compute morphisms from a Lagrangian to possibly coisotropic. And that's the thing that it's symplectic geometers haven't told us how to do that. So,
No, but he's saying for this proposal,
yeah,
which you pushed through,
yeah,
right? Do you have a composition?
Oh, the composition. Is that, oh, I see.
Yeah, I mean, the question is whether you can define now some category, perhaps not the conjectured one, but can you define, I mean, I don't know if it makes sense to consider some toric geometry and so on, this is all some extra structure, but perhaps adding, not considering the most general objects, considering rather special objects, or so perhaps on the right, the definition of some category which has really morphisms.
Yeah, I think so, because so we have also a proposal for the morphisms, and it kind of it's like when you have a monoidal category, you kind of have two directions of composition, the usual composition, but also like the tensor product. And that will give these, that will kind of allow us to compose. We're kind of using the tensor product structure to define the composition.
So for that infinite family of objects, the BK that you produced,
yeah,
there's morphisms between those, and the composition of those recomputed.
Yeah.
And so, and it forms an algebra, and so it is a subcategory, basically.
Yes,
yeah, that's right.
You can consider it as a subcategory of some
Undefined, yeah.
Yet undefined.
Correct.
Yeah.
It's very nice.
Yeah, if you have now a generalized Kähler structure, if you have a guess for how the two quantities are related, the one of one GC and the other.
Well, I'm not sure. I mean, so generalized Kähler structures of symplectic type are kind of equivalent to like one of these spaces, right? With L is like a generalized Kähler structure of symplectic type. So in some sense, we're doing geometric quantization of that symplectic form, and we're using the other GC structure as the polarization.
Yeah, and now if you reverse this process, it's clear how these two quantities are related.
No, because
should they be related?
I'm not sure.
It's like saying, like, take a Kähler manifold and look.
Complex and symplectic, right?
Yeah.
Should be rated to the mirror. Yes.
Yeah, it's unclear here.
Any other question or comment? No, let's thank Francis again.